Okay, so last time we have finishing the squeeze theorem for sine x over x. Okay, I mentioned before you can also do the second way. Okay, it is based on this three triangle. Okay, this is the first triangle. This is the second area. Um, in math, we call this area called a sector. Okay, so sector is like when you slice a pizza, that shape we call it the sector when you cut the pizza. Okay, so it's sector. So you have the small triangle, sector, and the big triangle. So OBC, OAB, OAD. Okay, remember that area of triangle is half base height. Okay, and how about area of sector? Okay, because the whole degree for our angle in circle is 360 or 2 pi, right? So the area of sector is its angle divided by 2 pi multiplied by pi r squared. It's logical, right? So the angle and then divide by the whole angle and multiply by the area of circle. So you get half theta r squared. Okay. Okay, so from this okay, if you see they are all connecting to B. So maybe you cannot see here, but this is B is here, right? From the picture. And this is C. So all the line connecting to B, that's why we can compare all these three, use the squeeze theorem. Okay. So let's try to look at the small triangle OBC. So OBC will be the area OBC. Wait, OBC is half I can make because it's the same triangle, I can make OA. Okay. It's the same area as the triangle. Okay. And we know that from our previous sine theta is BC over OB. So we can conclude that our sine theta is just BC. And OA is also the radius, r equal 1. Okay. So this triangle OBC will be half sine theta. Okay. Let me write this as 1 and then 2. Wait a moment. And 2 is the sector OAB. This is half theta. Because the radius is only 1, they just half theta. Okay. The third one is the triangle of OAD. So it will be half OAAD. Okay. From previous, we also have connection with tangent theta is AD, right? So we can just say this is whole tangent theta. Okay. So we have at least function in theta, half sine theta, half theta, half tangent theta. And from geometric perspective, this is small triangle OBC. Okay. this OBC is smaller than the sector is smaller than this one. Okay. So if I write here, okay, so triangle OBC is smaller than sector OAB, smaller than triangle OAD. Okay, I'll write in the next page. Okay, let me continue. So sine theta over 2. To make sure that this is all positive, okay, I just making sure and just adding absolute value in case something goes wrong. And you can do that if you know that your functions or your calculation will be positive. You can also make sure that you have absolute value. You can do, okay, as long as it is according to the procedure. And then, and let me write this as equal, okay? It can be depends, okay? Okay, I will multiply all by sine theta. Or maybe I will remove the 2 first, multiply by 1 over sine. So I will have 1 theta over sine theta. And this should be 1 over cos. Okay, because we already have our functions that we want to approach here, but it seems flipped, right? So let's reciprocate all of this. Reciprocal. And then it will be 1 and then approach the limit as theta going 0, 1. So 1, it's also 1, right? Cos, or I will write cos 0, it's 1. So by Squeeze theorem, or if you want to add for theta from 0 to over 2. Yeah. So you can have 2 methods at least for sine x over x equal 1. personally, I prefer the area one because I can see the area. But if you prefer the first one, that's also fine. But at least, okay, at least if you see any limit x as approaching 0, you can definitely answer this is 1. Okay, you don't need to prove anything. Okay, if you see in other problems and you see this appears, you can conclusively equaling 1. Okay, so maybe you have limit and maybe it has a complex trigonometric. When you are trying to solve, maybe you find this sin x over x and limit x approaching 0, you can equaling this as 1. Okay. Okay, for online students, do you have any questions? Any questions, online students? So far, you understand the content? Okay, you mean the previous page? Okay. I will show the previous page for a moment. Okay. And don't worry, after we finish every chapters, like this is chapter 2, because chapter 1 is like reviewing functions like a really basic. So after chapter 1 and now chapter 2, after finishing chapter 2, I will upload the PDF file of all these notes to the Moodle. Okay. So if you need to review. Oh, yeah. Wait. Okay. This should be this. Okay. Sorry. Right. Correct. The triangle. But the uh, okay, should we remember this theorem or you just want to let us know limits sin x over x is 1? I don't want you to memorize, but I want you to know the logic. So if you want to prove, you can do it by yourself. So it should be not OBC, but OAB. Sorry. Yeah, so the OBC is actually it should be the OAB. Okay. Okay, but the rest is practically uh, practically correct. Yeah. Okay, from all of you, any questions so far? Okay. So every functions that you can find any point that at one point that functions has the same value, you can use the squeeze theorem. Okay, squeeze theorem. Or any function you find, you know that there's 3 functions. If you want to know the middle functions, you can check the first and the last if they both the same functions, and you know the middle function is in between those functions. Then when you find the first and the third the same value, then the middle also the same. Okay. Okay. So from here we can also solve limit as x approach 0. So because we know that limit x approaching 0 sin x over x is now is equaling 1. So now we can approach this and try to solve. Okay. So let's try to solve this. And try to make it multiplying with the opposite signs. Okay. So I have the 1 minus cos squared x and then x. Okay. This part will be sine squared x. X and this is sine x. I will make separation here. And thus we can evaluate the limit. So I will write in, so limit x approaching 0. So this, the first part will just 1, right? And if you plug in here, it's 0. And this is 1, 0 over something, so over 2. So it's 0, right? So 1, 0, so this should be 0. So practically in any trigonometric limit function case, okay, problem, when you find any limit as x approaching 0, sin x over x equal 1, you can equaling this into 1 and solve the problem. Okay. This is just one example. Maybe we'll find another example, maybe in your TA class. Okay. Okay, that's all for squeeze theorem and some additional notes. Um, I think we now will be going to a section called precise definition of a limit, or uh, limit in epsilon and delta definition. Okay, the sections is, maybe you will find weird at the beginning. Okay? Because when I was in undergraduate, I also don't understand. But hopefully you can find this is interesting. Okay. Let me start with the new page. Okay. Let me draw some maybe here's, oh. Okay. This is a function. Okay. Based on our definitions, okay, based on our definitions, if we have functions like this with a hole, okay, when you plug in the number, it will be undefined. But when you are calculating the limit as x approaching a of x, f of x, it will have limit, right? So the section or the whole section about epsilon and delta is how precise. Okay, limit is actually about we are getting closer, 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 right? But how close is it? Can we make some small number and prove that okay, this is true, that this is going really small, and we want to know how small. So I will start to write this. So precise definition of limit, or we call this epsilon and delta definition. So the epsilon, this is epsilon, this is delta. Okay. Okay. So what does it mean? Okay. Let me draw something first from the graph here. So if you have some number closer to a, that will be counted as your limit. For example, like from here to here, it's quite big. But actually, imagine this is really small. Imagine this is really small. So the delta is the distance between a and this interval. Okay. So this is a minus delta. This is a plus delta. This area here. Okay. So when you are dealing with delta, it will also affect the f of x. So you can have from here, the L also change in a small number also. We call the number epsilon. So this is L minus epsilon. And this is the plus epsilon. So again, epsilon and delta is a distance, okay, from A and L, okay, to some small number. Okay. Let me write some words first. Okay. So let f be a function defined on open interval contains number. I will make a different color, A, this A, okay, except maybe or possibly. Yes, same, possibly uh, at A itself. It's precisely the same as the picture above. Okay, so we say, okay, so we say limit of f of x as x approaching A is L, or if you want to write in math notation is this. So if, okay, so this is the definition. So if for every number of epsilon greater than 0, so epsilon and delta is just a distance, okay? It needs to be positive, okay? So there is a number such delta that if, okay, that if we have a distance from x to a. So the delta will be around this x to a, and then okay. So what does really mean? Okay. So so by definitions, okay, if you have any functions like just linear functions, easy functions like 2x plus 5 or 2x plus 3 is your functions, then you need to prove some delta that you need to find, and then when you plug in the delta, it will become this definition. It precisely fit with this definition. Okay. I will show you some illustration and how to solve problem. So usually problem within this precise definition of limit is to show or to prove whether you can get the epsilon and delta relations or not. Okay. Usually the function is not really that high level functions. Usually just linear, quadratic, but you need to understand the logic behind all the process. Okay, so the epsilon and delta is actually just the last part here. This is the epsilon delta. This part is just regular, just regular limit here. The epsilon and delta definition is here. The words is here. Okay. You don't need to memorize. Just understand what it is. Okay. Okay. So I will write. Okay. I will write that epsilon and delta is actually uh, maybe notion of a closeness. Okay. How close it is to how close it is to x or to the f of x. Okay. So if you have this is f of x. Let's say your f of x is maybe 7. Yeah, any functions, and then maybe equaling 4. Okay. Or maybe, yeah, just maybe 7. Okay. Okay. So if you take a number close to a, close this to 7, you will have this small number around this 7, and it will impact the f of x. Okay. So do you have another interval here? You have another interval here. So, for example, okay, if you have the distance, maybe the distance is really small. Let's say 0.01. What does it really say is you have then it will be 6.99, right? And this should be 7.01. So to illustrate, this is your interval here. So any number in this interval will satisfy okay. And then you can check 0.0001 and so on and so on and so forth. But this is just an illustration. Okay. What will you do is you need to find this 0.01. Not find, but try some logical number that when you plug in, it will prove the original functions. Okay. Maybe let me just show you how it's done. Okay. Okay. Let me go to the next page. Okay. Proof limit as x approaching 4. Let's just start with really basic so the question is prove this limit, okay, using precise definition of limit. Okay, it's pretty logical. Like we have done how to evaluate limit. When you have a limit, you have x approaching something, you direct substitute, done, right? But it's already there. The answer is already there, and you need to prove by using precise definition limit. What you need to do by proving this is you need to find some delta and relation that delta to epsilon, and then prove that the delta with the relation of epsilon is basically true. Okay. So you need to show that okay, if x minus a is less than delta, then f of x minus L less than epsilon. So basically, you need to find the relations. Okay. I will start with the. So this is A. 4 is A, right? This is the L. Okay, this is the fx, right? So basically, when you say f of x minus L less than epsilon, you need to write 2x plus 3, that's the fx, minus 11, that's the L, right? And this should less than epsilon, right? And then we need to write also the distance of x. So the distance, this distance should be less than the delta that we need to find. Okay, so from the 2x plus 3 minus 11, we can solve 3 and 11. Okay, And from there, you know that it is x minus 4 is less than epsilon, right? And you kind of figure it out easily because this x minus 4, oh, actually that's the same x minus 4, right? Then you found these relations, okay? You found these relations, okay? And then to make it true to what our needs, okay? We need to decide. We need to decide, okay? Because we have this epsilon over 2 here, okay? We need to decide. So let's just say that let the delta be epsilon over 2. So this is our relations, okay, between delta and epsilon. So we need to use this delta, bring back this delta into our equations. Okay? So from x minus 4 less than delta, okay, we substitute the delta with epsilon over 2. Okay, so it's like moving forward and then going backward. Okay, reverse. Okay, so we have this is 2x minus 4 less than epsilon, and now we have 2x minus 8 minus epsilon, and then going here, we can change the form. Minus 8 become the our original equation at the beginning. So we can make it plus 3 minus 11 less than epsilon. So when the delta is epsilon over 2, we are going back to our original equation, which means, okay, which means this is fx minus L less than epsilon, or I will say then, which means we have when the delta, let me write, when the delta is epsilon over 2, limit has been proven. Or actually, you can say also using the QED or just like words, it has been proven that this limit is true, or yeah, any word that conclude that you have proven all of this. Okay? So there are, I think, only two parts that important here. So this part, okay, I call this part is finding the delta uh, and relation with the epsilon. And then the second part here is the proving the delta. So first you need to find the delta, what is its relation with epsilon, and then plug in back and return to original equations. And then another notes, okay, another notes that you need to, maybe it's important. I think it's important. So delta, it depends on epsilon, but it cannot depend on x. So what this note means, okay? This note means, okay, you need to find the expression delta and epsilon exactly like this, okay, or similar like this. So you don't, or you cannot have any x in epsilon. So if you have any x here, then your delta is actually is not correct, or it will be proven wrong because it's having an x. Okay? Because we need to find the exact number. That's why we call the precise definition. So we need to find the exact number between delta and epsilon. Okay. Okay. Let me show you what does it mean. Okay. In another example, and then after that, we can move on to another page. Is it too small? My writing? Can you still read? Okay. Can you still read or too small? Too small. Okay. Okay. Let me brief once more to you. Okay. Okay. If you want to prove this whole limit, okay, limit as x approaching 4 to x plus 3 equal 11. Of course, if you see the limit, when you plug in 4, you can evaluate directly, right? Easy if you just need to find the limit. But it's already there, 11. What you need to do is, can we prove this limit based on our understanding on uh, epsilon and delta? Okay. So we need to show that, okay, if x, the distance, okay, from x to a is less than delta, okay. When this happens, this f of x minus l, or the distance of the value of the limit and the functions, is less than epsilon. So we need to find relations from here and here. So when we have our delta, when we try our delta, it will be proving the epsilon here. Okay. So we are starting from our functions. This is f of x to x plus 3. 11 is our L. Okay. So f of x minus L here. It needs to be less than epsilon. Okay. We see that actually it has 2x minus 8, and we can factorize. We see it has similarity. It has similarity, x minus 4, with our distance here, right? Okay. So we can say that our x minus 4, or the distance, is epsilon over 2, which means we can use this epsilon over 2 as our delta. We find our delta, okay? And we use our delta epsilon over 2. We use this epsilon over 2, okay? And trying to simplify, and we are going back to 2x minus 8. And then we can also separate, making the same original equations. Okay. So by these functions here, or by this expression, we are proving that with the delta equal epsilon over 2, we are proving that this limit is true. This limit is true by this delta epsilon relations. So the important thing is you need to find delta and epsilon relations. Okay? And one more thing is, in this expression, epsilon over 2, when you are trying, maybe solving another problem, you find x here, you need to remove that x. There are several ways to remove it. Okay, I will show you in a minute. Okay. Okay, let me write another. So limit x approaching 1. X squared plus 3 equal 4. Okay, we need to prove using, or I will just write epsilon and delta. You can try, but you will find it has a bit of problem. You can start with the writing given epsilon should be greater 0, delta also greater 0. That's also you can do. And you can also start with the delta here. And also start with the epsilon. So x squared plus 3 minus 4 is less than epsilon. And usually we are started from the epsilon, and then we find some relation with the delta. We use that delta and prove and bring back the original equations. So from here, you will find that this is x squared minus 1. Let's try to factorize this x plus 1, x minus 1, right? What we want is the x minus 1, the distance, right? But when we approach or we simplify this, we have this, right? We have this problem here. That's what I called before in the notes. We should not have any x here. We need to remove all x. So it should be delta, epsilon, and any constant number. So what you need to do here? Any idea? So let me draw some line here. This is 1. Okay. Let me draw this is 1 minus delta. This is 1 plus delta. Okay. This is delta. Okay. Let me remind you that the delta is really small, right? Okay, so when you are dealing with the distance between x and 1, when you say it's less than delta, we can simplify the delta as any number as we want, as small as we want. Okay, it can be 0.1, 0.5. But for proving this equation, let's just say less than 1. 1 is our small number here. Okay, let's just say assuming less than 1. Okay, I can rewrite this inequality. Okay, removing the absolute value, and it will be -1 here, +1 here. Okay, I will plus 2 to all number here, and you will see 1, x plus 1, 3. Okay, I'm plus 2 to the all number. Okay, and then I will reciprocate. Okay, it become 1 over 3. This is 1 over x plus 1 less than 1. Flipping the fractions. Okay. Okay, let's try to multiply all by the epsilon. So epsilon over 3 is less than epsilon over x plus 1 is less than epsilon. Okay, we get this expression here. Okay, and then I will write here the epsilon should be positive, right? Because it's distance. Okay? So let epsilon be positive number, and we choose, okay, and choose the delta as minimum as possible, okay? Because we want the delta as small as possible. Okay? The delta minimum from our inequality, okay, here. Let's say because we are already make this, the maximum number is 1 here. Okay? So the delta should be less than 1. So the possible delta, okay, the possible delta is from here, okay, epsilon over 3, okay, from epsilon over 3 until 1. We choose the delta minimum, which of course the epsilon over 3. Okay? And suppose, okay, I will write back all the information from the beginning. So suppose that the distance is less than delta. Okay? And because we are choosing the delta minimum from our interval here, we are choosing the delta to be epsilon over 3. Okay, I will write here, choosing delta is epsilon over 3. From here, okay, if you remember, when you have x minus 1 is less than 1, when you have x plus 1, it's less than 3 from that equality. Okay, so or then maybe then. So then x minus 1 multiplied by x plus 1 from our definition above, okay, should be less than this epsilon over 3 and 3. Okay? That is why our quadratic function here, or this is the x squared minus 1, but I'll write the back to original equation, is less than epsilon. So by choosing delta 3 from we or limit has been proven. Actually, the conclusion can be any words you want, but it should be conclude the results that it has been proven by choosing some delta. Okay. Okay, so what we are doing here is we want to make sure that we know that this x plus 1 need to be removed. Okay? We need to find any small number. Okay? That's why I try to manipulate from the x minus 1, this one, okay? And then try to find any relation with the x plus 1. And I find this inequality, which I can manipulate and looking for possibility in between some interval. Okay, okay, this number 1 here, okay, number 1 here we can choose any number we want. But if we take a look to make sure that the equation goes well, that's why I'm choosing this one. Okay. So this number one is not from uh, this not from any information from question. This is our assumption. Okay, assumption. This is assumption. Assuming, okay? Assuming that the distance really small. Okay, but if we use this one like 0.1, 0.001, maybe we will make some mistake in the equation. So that's why I'm choosing one to make sure that it reduce any mistake. So the idea is just finding delta in relation with epsilon and then proving the delta. So it's like moving forwards, backwards. It's not really finding any, like usually you find limit, you evaluate the limit, you find the solution, right? It's not finding the solution, it's finding the proof. Okay? So you need to move forward, backwards, and then proving the original equations. Okay. Okay, any questions? Confused? It's like going forward and then back to the original one. Okay, any questions? If you are given the problem, I hope you get the idea. Okay, the idea is first finding the delta, proving the delta. Okay, if there's no questions, online students, do you have any questions? Any questions, online students? No? Everything clear? Mm, okay. Okay, let me uh, go to the next session. It will be about the continuity. But maybe I will start with discontinue. But the section will be continuity. So I will draw. Okay, we know from previous session that this kind of functions, it has limit, right? Even though when you plug in the number, it will be different from the limit value. First, we need to call what's the definition of this discontinuity. This is called removable point or whole, okay, discontinuity. And then another case, this is we called jump discontinuity. You don't really need to memorize the name actually, but at least the graph is makes sense. But here at the A, there is no limit, right? Because okay, let me write here limit. When you see jump, uh, it's obviously not continuing the line. Okay, and then another one. Mm, you have the asymptote. So A. Okay. So limit x A minus is, we say, you can say it's going to negative infinity, or yeah, just write this. Okay. Or what I write unbounded. Unbounded meaning it's getting larger and larger without any limitations, going to negatively infinity amount. This is unbounded to positive sides. But because it's going different way, there is no limit. Okay, in approaching the A, there is no limit because one from left and from right is not the same. Okay? So there is no limit. Okay? So it's quite short continuity because all of the idea is from the limit. So should be quick. Okay. So what continuity means? Okay. The simple way, if you cannot find any discontinuity, that's continuous. The simple words. Okay. So when you plug in the number, it's the same value as its limit. That's continuous. Okay. Like for example, the first one, you have a hole, right? So when you have limit as x approaching a, it's not the same as fa, right? From this graph. But when it's equal, that's continuous. Okay. Okay, first whole discontinuity, jump discontinuity, asymptote. Okay, at least we have these three cases. Okay, let me write in the new page. So continue means, okay, let me draw. Let's say C. So this is f of x. So the function is continuous at x equals c if, okay, limit x approaching c is the same as f of c. This is the um, formal definitions. And then the other part is if you have some interval. Okay? So continuity. So continuity over an interval. So f is continue. I will just write continue like this to make it simpler. Over some open interval a. Let me write a b in red. Okay. So this is the first case, the open interval. Okay. The second case is f is continue over interval, close interval. So f is continue over a b open, but you need to have proof that the limit, the value should be f of a, and limit from left, from, yeah, correct. Yeah, because it's from inside to outside. So f of x, this should be. So what does it mean? If it is just an open interval, then you just say that every point over that interval that is continuous, right? But when you say closed interval AB, So you need to prove, okay, first is over this AB, every point is continuous. But also when you approach this A from right, okay, A plus, right, and B from left, this should be, the limit should be the same as its value when you put in FA and FB. This is the definition for a closed interval. So at least you have 1, 2, 3. Because maybe the function itself, maybe the whole function is not continuous, but in some interval, maybe it's continuous. Like you have jump, but if you just look, maybe just a small part, it's continuous. But the whole function, maybe it's not. We'll have maybe one example, and then if we have still have time, there's one more I forgot to mention. When uh, limit as x approaching infinity, I think we haven't discussed that yet. Okay. Okay, any questions first? Online students, do you have any questions? Okay. I think this is clear, right? I think high school also, right? Or no, just a slide similar high school. No? High school? Continue function, right? Yeah. Okay. If you have consider function what value should be assigned to f to make f of x continue. Okay. First, do you understand the questions? So let us see the questions. Okay. So this is the functions. Okay. So this is the functions. 6x squared plus 18x plus 12x over x squared minus 4. What value should be assigned to this function if you plug in -2 to make the function continuous? Okay. Remember that when you evaluate limit, okay, when you evaluate, when you substitute um, x equal -2, substitute, okay, your function, okay, from based on this definition, what will happen? 24 become negative 24, negative 6 plus 12. It becomes 0 over 0, right? Okay. Like I told you before, the function here, okay, it can be undefined and it can be defined. So actually, the question is asked, okay? This is what you need to do. We need to simplify the form and try to, maybe we can factorize this and find the real numbers value. So let's try to solve this first. X plus 1, right? So we are canceling this part. So we have f of x now, or let me write in different function. Let's write g of x. But let's write just f that defined. For uh, for x not equaling plus minus 2. So f minus 2, it will become 3 over 2. So this is the value that we need to assign. Okay, so this undefined is when this is x 6x squared. Defined is 33 over 2. X equal negative 2. Okay. So this is the, I think, typical questions in limit, especially in continuity. I think if you do not have any problem with your algebra, solving equations like this, it should be not a really hard problem. Okay. This is value that need to be assigned. Yeah, it's also undefined. But because the question is specifically asking -2, then we just calculate -2. Depends on the questions, actually. So um, it can be, or it has some variations, okay? But mostly, this is the typical questions. Another variation is if you have incomplete equations, like for example, maybe um, it's not 12, maybe it's k, maybe h, right? And find the value of h. But how you solve is the same way. Like for example, you have h, but you know the value. You just need to reverse the whole uh, solutions. For example, you have a quadratic functions, but some coefficient is unknown, like h or a, and you need to find that a or h here. Maybe like x squared plus ax plus, let's say, 8 over some x minus 4. And then you need to find a. How to solve this is basically a similar way. Maybe later you can have some exercise and also some explanation from your TA. And I will also send some maybe some PDF file from exercise from the book. Okay, so you can at least take a look what kind of questions you might have. Okay.
Wrong. It's x plus 2. What is x
Mhm.
minus 2?
Wait. Oh, wait. It's not x plus 2. Sorry. Should be x minus 2. Sorry. Okay, good. Okay. But that means you pay attention. Okay. Okay, if you have find some mistake, you can ask me, okay? Sometimes I have a typo. Okay, I will just go to the next page. One more session. And if I think maybe we need to have some more, I will continue next week. Okay, I will go to the next page. So I forgot to mention this last time. So we have also limits at infinity. So if the function defined on, let's say, a to infinity, the interval, we can have limit as x approaching infinity of some function of x. We can have some value L. So means f of x can be made closer to L by making x closer or sufficiently large numbers. And also, if your function defined on interval from negative infinity until some number a, you can also have limit as x approaching negative infinity of f of x. This is also L. Same words, but a sufficiently large number in negative numbers, okay, large in negative numbers. So the line, okay, so you have line y equal L. So for example, you have maybe like that, and you have line here. So you have this red line is your horizontal asymptote. Okay. One more page and we can finish. So uh, I'm not sure if you still remember this expression. So if, okay, R is greater than 0 and rational number, then the whole limit, this limit will be 0, right? Okay, remember? So when you have this type of questions, what will you do? Divide by the largest degree, right? Largest degree. So if we see here, we have squared, squared. There's no greater than squared. So divide all by x squared, right? Okay. So this is becoming 3 minus 1 over x minus 2 over x squared. This is 5. And the whole here, because we have these definitions, this becomes 0. Okay. So you can conclude this 3 over 5. But maybe later I will take a look in more details if we have time. But at least for limit at infinity, you have the horizontal asymptote, okay? And for 1 over x, any polynomial, okay, it will becoming 0, okay, if it is rational number and positive. And also another possibility, we also can have limit x infinity f of x, and it still can be just infinity. It also has this possibility. Okay? Also, at least four possibility. Okay, we can also have this possibility. Oh, I think one more, but I think next week. One more, just a short one, and then we can move to chapter 3. Yeah, online students, do you have any questions? Yeah, Tong, what's your questions? Uh, Wait a moment. This one or this one? Okay. Any questions from this part? This? Which one? Which one? Which part is blocked? The bottom one? Yeah, it's just the value that need to be assigned. Just that words. Here, it's clear. No. Oh, okay, okay, okay. Okay, now, any questions from you? Any questions? Okay. So far, it's actually some of your high school, right? High school limit, right? Okay. So yeah, I think doing like I have online students and then offline getting work at the same time is quite exhausting. And honestly, I feel bad for all of you because I can make like 100% teach all the material. So at the very beginning, I said to you that maybe we will take us really slow, okay? Take a really slow. And if you have like any questions, maybe you are not sure in the class. After the class, you can ask, okay? Maybe in the class, it feels awkward, like I'm still explaining, and maybe you don't want to trouble me when I still explaining something. You can ask like after class, okay? Or maybe if you want to email or using the Moodle to ask something, you can ask. And also regarding the quiz, okay, the quiz is just the chapter 1, chapter 2, the functions and limit, okay, just that part, like limit, maybe some concept of limit. When you have like a discontinuity, that's also limit, okay. And maybe we will have around middle of October. And maybe it just take around 30 minutes for the quiz. So maybe we will have a class first and then quiz, or quiz first and then class after the quiz. It can be the Tuesday class or Thursday. I'm not sure if my content is um, understandable or made some confusion because I don't know. Is it too slow, too fast, or because I feel maybe some part is too slow and some part is too fast. What do you think? It's just fine or fine? Okay. Okay. If you have any complaint, just ask me. Okay. Okay. If there's no questions, I think today will be until here. Okay. So class finished. I will send you later some PDF file. You can take a look. Okay. You don't really need to like working all the parts. Okay. One thing about math. Okay. I think you asked me right whether it is good to be have exercise or not. It's good when you understand. If not, any exercise memorizing the solutions is not good method. Okay. But when you understand the problem, you understand the solutions, then it's good to be having exercising. But when you don't have enough concept, you try to exercise, you will not get the good result. Okay, 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 class finished. Okay, thank you, online students. Okay, I will explain to you about the quiz. Okay.
My office is
Oh, uh, it's should be OBA. Sorry,
oh
sorry.
is OBS.
Yeah, OBA, OBA. Okay, sorry, sorry. Yes,
Acknowledge
yes. Moodle.
and
Sure.
video can also.
Yeah,
Oh,
yeah.
thank you.
Yes.
That's so cool. Say, and may I scan
Yeah, yeah, sure, sure. I will also ask the student. Okay, if you need the QR code, you can still scan. Okay, online students, you can also scan if you haven't scanned the QR code. Okay, if you have scanned the QR code, you can just leave the meeting. Okay.